Welcome to lecture 5.7. Here we're going to discuss the substituents on chairs and how we can understand them compared to the flat projection. So looking at the flat projection first, remembering that we're dealing with alkanes, which are sp3 hybridized. Here we're going to draw each carbon with two straight lines, one wedge and one dash, like we see here. Now every carbon is going to have these substituents, but I've only drawn these two to keep it a little cleaner. Now when we're looking at the flat projection, we get information about what's going towards us, that is the thing on the wedges, and what's going away from us into the page, which is the things on the dashes. Now, sometimes these are referred to as the top face of the ring and the bottom face of the ring. So in this case, things on the top face, we always have this perspective that we're looking from the top of the ring. So if we imagine the ring as flat, we'd be looking from the top face. Things on wedges would be coming out towards us, and things on dashes would be going away from us into the page. With that in mind, wedges represent the top face, and dashes represent the bottom face. Now, there is such a thing as cis and trans when it comes to this on the flat projection. Here we can look at substituents A and C. We see that they're both on wedges, and so we can say that they're cis to each other. However, if we look at A and D, we can see that they're on different faces of the ring, as A is on a wedge and D is on a dash. That means that they're opposite, and we could call that a trans orientation. Now, this is useful, but how is this going to look on a chair? Because remember that the flat projection is a simplified projection. It's useful in some ways, but we do lose some structural information. Well, to understand this, it's important to first recognize that when we've drawn the chair, we have already drawn all 6 of the flat projection's carbons, and all we have left to draw is the 2 remaining substituents. Now, importantly, the wedge and the dash do not correspond directly to what we see on the chair, and that's why the chair is important to draw to understand the structure of these chairs. So each carbon in the chair is going to have 2 substituents. So each carbon has 2 substituents. Now, for each carbon, one of them is going to be axial, and the other is going to be equatorial. So, to be clear, that means that one carbon cannot have 2 axial positions. It's always going to have 1 axial and 1 equatorial position. Now, I highly recommend considering the axial positions first, as these are a lot easier to draw and easier to understand. The axial positions either go straight up or straight down. And we kind of view this, that's kind of why we have that name axial. We would say that it's on an axis, up and down. So each carbon is going to have that. Now, earlier I mentioned that with a chair, we can see that each carbon alternates going up and down. So for example, if we look at this carbon, we see that the bonds kind of are drawn upwards towards that carbon. But then if we looked at the next carbon here, we see that the bonds are drawn downwards here. So what does that mean for us? Well, when it comes to the axial positions, I'd say that if the carbon is going up, which in this case would be this carbon, and this carbon, then the axial position goes up, and vice versa. So here we can draw the axial positions straight up on these carbons and straight down on the other carbons. So we have 6 of our carbons, and you can see here that the axial positions don't necessarily correlate with the wedge and the dash. What do I mean by that? Well, if we look here and let's number some carbons, if we look at carbon 1, we can see that the axial position is going up. If we were going to draw that on the flat projection, viewing from the top perspective, we would say that this group is a wedge on that flat projection. So does that mean that all axial positions are going to be on wedges? No, it does not. Because if we look at carbon 2, we see that that's actually going down, away from us, and that would be represented by a dashed line. Furthermore, we can see that it alternates across the chair. Carbon 1 is up, carbon 2 is down, up, down, up, and down. So we can see that this alternates. Great, so these are the axial positions, and they're much easier to draw since they're going either straight up or straight down. Now the remaining position is the equatorial position. These they're kind of projected outwards, away from the chair. So away from the ring. Now, they can be quite difficult to draw accurately. My advice would be just to draw this a few times on paper until you understand and compare the proportions to a standard image. But to be more specific with it, on carbon 1, the equatorial position is going down this way, parallel to these two lines, so the lines that are one carbon away. Now, importantly, with equatorial positions, it can sometimes be difficult to tell if they're going up or down from the chair drawing. For example, this one, it might be clear that it's going down, but it's much less obvious than the axial position. My strong advice is to always consider the axial position when you make that assessment. So, for example, on carbon 1, we know that the axial position is going up because this is an up carbon, where the lines are being drawn up towards it. And that means that the equatorial position must be down. This becomes especially relevant here, if I number the rest of the carbons, on carbons 3 and 6, where the equatorial positions are parallel to the side lines of the chair. And with these ones, with this perspective, it can be very difficult to tell, just based on those blue lines, if those equatorial positions are going up and down. But if we look at the axial position on carbon 3, we can clearly see that it's going up. Therefore, this equatorial is moving downwards, and this equatorial is moving upwards. To draw in the rest of the equatorial positions with blue lines, I'll fill this in here. I'll remove the axial and equatorial text so you can clearly see where these positions look and what they look like when they're all drawn in. I would advise you to practice drawing this a few times just to make sure that you can get the proportions correct, because the cleaner you draw your chairs on a test, the more likely it is that you're going to get the marks for the correct answer, where even if you get the answer correct but the chair is very messy, it might be hard to tell and you might lose marks that way. So each carbon has one axial and one equatorial position, as shown here. And just like the axial positions, the equatorials alternate as well. As in, this one goes downwards. On the flat projection, we would see that as a dash. Upwards, we would see that as a wedge, and so on and so forth. Now, imagine we had a methyl group. So let's look at this molecule here. We'll look at carbon 1 and carbon 2. If carbon 1 had a methyl group going up, that would be axial. Carbon 2 would have a methyl group going up. That would be equatorial, since its axial position is going down. Now, how would that look on the flat projection? Well, we would see this methyl group going upwards towards our eye there from the top view, so we would put that on the wedge. Carbon 2 would also be on the wedge. So that is how we can handle the chair substituents there. So, excellent. Let's take a look now at what that would look like with the model kit. Here we can see that the red dots represent the axial positions, as they are all going straight up and straight down. And we can also see that the equatorial positions are kind of projecting away from the ring, as discussed. So that's how we can understand this 3D structure using a 2D drawing. And again, being able to do that is a core skill in organic chemistry. One last thing to talk about with these substituents is their stability. So here I've drawn a chair with only the axial positions drawn in. And we have a new type of strain here that I'm going to call diaxial strain. Let's say that we put a methyl group here on the axial position versus putting it here on an equatorial position. Now, this methyl group that's projecting upwards on the axial position is still pretty close to the ring and is able to interact with these other hydrogens. Let's draw that carbon-hydrogen bond out. And we can see that these hydrogens are pretty close together. So by being on an axial position, your substituents may actually interfere with other axial positions. Now, to be clear, an axial position down here would not interfere. So it's only when they're on the same face of the ring. In this case, these substituents are on the top face of the ring. This is called a diaxial strain, which is a type of a steric strain as well, right? These are the objects in space bumping into each other. As a rule of thumb, the main thing you need to take away from this is that equatorial positions are favored. That is, the substituents can be more stable if they're on the equatorial position when compared to the axial. So the equatorial position is more stable and more favorable. Now, this is going to be important for the last sub-lecture here, where we're going to discuss the chair flip and hopefully make sense of one of the more complicated parts of this unit. We'll also do some practice on converting our flat projections into chairs to make sure that that core skill is locked in.